show starter for this thing. Put up a TV we bought that's 65 inch, get it mounted and everything. It doesn't work. It's a Samsung 65 inch, right? That's what you get then. So they're sending a technician out, but now we have to pull it back off the wall. And I've got a torn rhombus muscle back here. And I'm trying to, on Monday, not even today, it's bugging the heck out. Anyway, so if I'm wincing, that's part of it. But anyway, so today I'm going to finish up this Chef filter design. Let me tell you this much. There are tools online that will allow you to design a Chevy Chef filter for any number of elements. You just put in the required ripple, pass band, things like that. We're just doing this for one reason, because apparently in microwave engineering, you should be familiar with this, at least casually familiar, because you use this a lot. I know he's not here, but he used it, and I think you mentioned you used it in your digital signal processing class. Chevy Chef polynomials are mathematical. I mean, they're large polynomials that have to do with minimizing ripple and actually the pass band. But there's a lot to this. What Dr. Wentworth's book does is just give you more or less a technician's chart on how to go about doing this. But it's still kind of important that you're aware of this. So that's the reason I'm doing this. I don't like to do it this way, but that's what I'm doing. I'm going to go through first. Do you have any questions? I'll start that one. Yeah. Did you have one? I figure this. We do a low pass, a high pass, and a band pass, and we talk about the two different types. You can have either the T filter, two elements in series, one shunted down the center, which is usually capacitive for low pass, or you can do the pi filter. If we do these, we'll call it a day. That'll be the last thing we talk about, okay? And then we'll take care of any other questions you have, or are there any other questions in general at all? Okay. All right, so let's see. I'm going to start this way. You know, when we talk about a filter in general, you're talking about something where this block diagram, it looks like this. I should have done this the first time. And you're going to have some load resistance, RL, and you'll have a source resistance here, RS, and then you're going to have your voltage here. This is what happens. And this would be the input, the in, and this would be the output, the out. When you talk about the insertion loss, that's really just 20 times the log of the magnitude of V out over V in. Now I can put it in terms of S parameters, but I'm trying to be as simple as possible about this. I think everybody appreciates that, right? That's insertion. Typically when you look at this, if it's a low pass filter, and this is where we start at, you're going to have something where you have an insertion loss typically about 0 dB, means no loss. The output to input is 1 for a low pass. Then you're going to come over here, and ideally you're going to hit, Wentworth's book calls it a corner frequency. It's really it's the beginning of its 3 dB frequency, where all of a sudden it starts rolling on. So really what happens is when you have Chevy Chef filters, there's going to be some amount of ripple, and they'll hit here, and they'll come down like that. If it's a first order, it's 20 dB per decade. Second order, 40. Third order, it's going to be 60 dB per decade. I'm just trying to give you some things that aren't in his book clear, at least in my opinion. So that's what we're really talking about. Now, if we're talking about a low-pass filter design for any of these things, you have to know the cut frequency, you have to know the percentage, or the amount of ripple you want, and the number of elements you want. Remember what I told you, the higher the number of elements, faster the roll-off is. Follow me on that, everyone? So, what I'm going to do is, did you all look at this homework? How many did? Just tell me the truth. You like that? If you didn't, I'm going to try to make sense of all this in a way that would be useful for your quiz on Friday. So I can't be more clear, but I'm trying to help you, but help me too. So if you look at 1015 for a second, we're going to do a low pass filter. This is example 1015. This is, I'm sorry, example 1015. We'll get to the problems in a second. For 1015, it says he wants an n equal 3. We did this last time. That's, the order is 3, means 3 elements, all right? And we can have either a 2 series inductors and a capacitor that shunts to ground, or, or we could have 2 parallel capacitors and 1 series inductor. We'll do both of them. So for this one, it's an FC, a cutoff frequency of 2 gigahertz, all right? And has a Z0, a characteristic impedance of 50 ohms, which is about typical for microwave. And they want 0.1 dB of ripple. That's just this, which is a very small amount of ripple. So it's a fairly flat filter. And these are the requirements. You look in the table, you'll have your books here. All right, if you look in the table, just look where it says 0.1 dB ripple. And if you go down there, this is one we did, you're going to see G1 is equal to 1.03, is it 1.5 or 5? 0315. G2 is equal to 1.1474. And G3 will be equal to G1. Now, I'm just putting these values down. This is right from the table. I haven't shown you the circuit or anything. We have 2 options if we want. This was a low pass filter, I believe. Yeah, it'll be a low pass here. We can do it 2 ways. And I'll put the circuit schematics over here. We'll get the element values for both. That way, this should help. So when we're doing this, low pass filter, 3 elements. We can have a low pass filter can either be this. Remember, a low pass filter will always have these series inductor parallel capacitors. This would be one version, or the other would be this version. Parallel capacitor, series inductor, parallel capacitor. All right, let's see now right here, and we'll do this one first. Then we'll do this one. Now these are low pass. Does everybody see this is low pass? You should be. If you put a load in here, any load at all, and you have a source resistance, and here you're going to have plus or minus Vs. You can see that at DC, the inductors look like short circuits, so the output is basically the voltage developed here. And if you didn't have a source resistance, output would be Vs. As you get to higher and higher frequencies, the impedance here goes to infinity, and the capacitor becomes a short, so you get nothing. It's a low pass by design. And if you look at this one, same deal. The capacitors at high frequency will short, so this will look like a short. This will be an infinite impedance, that'll be a short, so put a load on here. You can see that this too is going to be a low pass filter. Y'all with me? Now we're going to start with low pass and we'll transform it into high pass, but right now we're going to get the values for both of these. So for this one, we'll call this A and this B. Now for A, we've got these values. So this is technically, in his book, he calls this G1, this G2, and this G3. Now anytime you're dealing with this, if you're dealing with an inductor, the way you get the L prime value, and this is an intermediate step, it's going to be simply the value of that element, which would be G1. I'm going to do it this way. And it would be times Z0. Now that gives you, it's a normalized, it's because of the normalization. Y'all follow me on this class? Then if we want the actual value of that inductor, we take this and we divide it by omega C. So if we divide this by omega C, now we get L double prime. And that would be over here. This would now be L double prime. It'd be the same thing over here. It'll be the same. And do y'all follow me on this? This is just a simple method. It doesn't go through the science of why it works. It's just showing you this is the way we do it. So for this value, the L double, we have G1 here is 1.0315. Then I multiplied by Z0, which is 50 ohms. I'm just going to put it times Z0. And over here, I erased, no, I didn't erase it. Omega C is 2 pi times FC, where it's 2 pi times 2 gigahertz, or 4 pi times 10 to the 9. Now, if you do this calculation, you're going to get a value, and that value is 4.1 nanometers. That's in the book. This is an example in the book. Y'all follow me? We're going to do the second part over here in a second. So this is going to be 4.1 nanometers. That would go here. This would be 4.1 nanometers. This is going to be 4.1 nanometers. Now we're going to get the value of C. To get the value of C, it's associated with G2. G2 is here. Are you with me, everyone? It's not hard to see this, but you got to at least see it. So if I have that, to get the value of C prime, and he does this in an intermediate step way. It's not always done this way, but it's okay. So first he takes the value of that G2, and then if it's a capacitor, you divide it by Z0, not multiply it by Z0. So you're going to divide this by Z0. Y'all with me? Now that's the normalized value. Then you have to divide it by omega C to get the actual value. Take a look. So then you have to take this and divide it by omega C to get the value of C double prime. And if you do that, you can check me on this. I have I want to say it's 1.8 picofarads, and I mentioned last time that's a very small capacity. So I think it's 1.8 picofarads. So this capacitor would be 1.8 picofarads. Now this is a T design. It's just one of two designs possible. Now we're going to get the values for this. Okay? Everybody with me? Here, the first element, this is now associated with G1. This is G2, and this is G3. And this is an example in his book. And it's on page this is drill problem 1016 on page 586, I think. So now, any questions before I go on about this? It's straightforward and simple to do this. You just have to at least do it a few times to get used to it. Remember, the key stuff over here is getting the values of that L prime and C prime for the low-pass filter. After that, pretty much everything happens. All right, so now, over here, since G1 right there is associated with a capacitor, to get the value of this capacitance, I'll just call this C2, and I'll call this L2 and C2. To get this capacitor, first we take C prime, and that's going to be G1, and it's going to be divided by Z0, because it's a capacitor. Y'all follow me on this? Capacitor divided by Z0. Then you're going to divide that by omega C, and that gives you the value of C double prime. When you do this, can anybody do this for me? Take 1.0315 and divide by 50, and then divide by 4 pi times 10 to the 9. And tell me what you get. I'll tell you why, because this is a drill in his book. I did this, I got the right answers. I had a slight discrepancy in the second or third decimal. But just tell me what you get. If you work it, it helps, believe it or not, to retain information. 1.6 picofarads. All right. 1.6 picofarads. I think that's right in his book, if you look. It's a drill in 16. It's on page 568. Is that right? Did you get 1.64 picofarads? Or just 1.6 period?
1.64.
Okay. He has 1.64, so that checks that box. Now, over here, we're going to get L2, but we start with G2. All right? So here, our L prime is equal to this G2 and it's times Z naught, because it's a series inductor. Inductors are always gonna be multiplied by Z naught, capacitors always divided by Z naught. Then, we simply take this, and we're gonna go ahead and divide it by omega C. And that will give the value of that inductance. Can you do that for me? So G2 is 1.1474 times 50 over omega C, 4 pi times 10 to the 9th. What do you get for that? 4.56 nanometers. Right. Is that what he has? All right. Now, that's going to be, by the way, this element will always be the same as this element, unless this load was different than this, but you won't see that, not in this class at least. And this element is always the same as this element. So whenever you have this and this, you automatically have that. You're done for third order filter. Okay? So that's the two ways to do a low pass. Okay? Now, next thing I want to do is just high pass. Now, is this making sense to everybody? I'm just going through this methodically. I don't want to confuse anybody. So, next is going to be high pass. And all these things start with a low pass design. And for high pass filters, let me just show you this. There's two ways to do them. You'll see the parallels. So, we have high pass filters. Again, two ways. One way is this: capacitor, inductor, capacitor, and then you'll have your load. And you'll have a source resistance, and then the actual source voltage. Now, if you look at this for a second, just always do this in your mind. Take a look at what this circuit looks like as frequency is 0 hertz and as frequency goes to infinity. So, at 0 hertz, a capacitor has an infinite impedance. Y'all agree with that? That's an open circuit. That's an open circuit. The output is 0. When the frequency goes to infinity, theoretically, capacitors look like short circuit, inductors look like open. It's definitely, if you think about that, a high pass filter just by looking at it. Y'all follow me? Now, next, that's one. We'll call this A. And for B, it could be this way. If you wanted a high pass filter, you could have an inductor here. This is going to be the pi filter, but now where the inductor and capacitors where you exchange the places. This will become a capacitor, and this is an inductor. I have one comment about this. Remember, that's an inductor, that's an inductor. There was one thing I told you about inductors that you should be aware of and not do. Remember what that was? Don't put inductors in parallel. Because a DC, you can't, if for whatever reason, if this was feeding the front end of a bipolar transistor, all right, where there's a DC offset bias, you all know how there's self-biasing with resistor numbers. This thing's going to look like a short. It won't work. That's why, I mean, you can build filters this way, but if they're feeding actually a bipolar input, not a MOSFET or something like that, then you're going to have problems right there. And even MOSFETs have self-biasing stuff. So an inductor in parallel is not a wise thing to do if you're feeding any kind of transistor input to a chip that has transistors or anything like that. I'll say one other thing. I don't think I've ever seen this filter design used in a real network, this particular one. I've seen this one used, but never this one. I'm just telling you that right now, just for you. But anyway, we're going to do both of these. So these are high pass filters. This will be D. So in his book, he says start with a low pass filter design. I'm going to start with this one, but it's going to be for a low pass filter. And the only thing I'm going to do is this. Just like he does in his book, this is Vs. I'm going to have some value G naught, which is going to be 1. It's just a normalization. You take the series resistance and divide it out, it becomes 1. And don't worry about that part. Now, here, this is going to be an inductor, and I'll get to that value in a second. This will be a capacitor, so I'm gonna start with a low pass design and turn it into a high pass. Are you all with me on this class? So, for this one, might as well do the same thing. Actually, I think this is example 1016. Modify example 1015 that we just did to design a third order high pass filter with 1 dB of ripple at 2 gigahertz. So all the conditions from the last one are going to be used here. And he shows on 588, he starts with a low pass filter. And here, this value of G1 is just the L. G3 is equal to, L is equal to G1, and here, G2 will be capacitive. So I'm going to start with this. I'm going to tell you for this stuff, we're going to go ahead and get the L prime and C prime as before. As a matter of fact, when we look at this, I'm just going to leave that as G. I don't want to confuse you with this thing. So if we look at just this low pass filter design, so we wanted to calculate the value of this L prime and this C prime. Well, for that, we would take L prime would be equal to simply that value of G1 times Z naught. You all follow me? That's just the normalization constant times the value looked up from the table. You with me, class? You take that, and then once we have this, to get the value of C double prime, the actual capacitance, and this is in his book, that's going to be 1 over omega C L prime. It's just an inversion. So we're going to take 1 over omega C L prime, or that's going to be equal to simply 1 over omega C times G1 times Z naught. Now this is again for this element right here, and for this element right here for a high pass equivalent, where the cut frequency is the same point as before. You all with me? 3 dB. So if you take a look at that, what is that value? Well, it's 1 over 1, 4 pi times 10 to the 9. That's times G1, which was, what was it, 1.0315, and then it's times 50. So, can anybody give me that value? And that's actually C double prime. Remember, high pass, you still get the values for L prime and C prime, and then you use those to get the actual values of the dual component by doing this little trick. 1 over omega C L prime to get C double prime, the actual capacitance. Anybody? 1.54. Picofarads. Now this is in his book. He has 1.5 picofarads. I don't know if it's around here, or if he just letters 1.5. You got 1.54?
Yeah.
Okay, I'm looking at his book on page 588. He has 1.5, but he's using the same calculation as I am. So I guess he rounded it. That's the only thing I can figure. So L prime, now the next thing we have to get this C prime here. Now remember, C prime for this one was simply going to be the value of G2, right, divided by Z naught. So we need that value first. Y'all follow me again? What I'm doing? G2 was what? 1.4747, I think? I have it written down here somewhere. 1.147, sorry. 1.147. 1.14747 divided by 50, so that's going to be C prime. And then to get the value of L prime, or L double prime, that's gonna be 1 over C prime, and it's gonna be divided by omega C, and, he shows that in the book. So this is gonna be 1 over, whatever this value C prime is, so that's 1.14747, and it's that divided by 50, and then it's times 2 pi times 10 to the 9th, or 2 pi times 4 pi, pardon me, times 10 to the 9th. Can you give me that value too? It's 0.023 times that. I think it's 3.468 nanometers. 3.468. Okay. So, this would be the value of the capacitor right here. The C double prime would be equal to 1.54 picofarads. And the value of that inductor would be 3.468 nanometers. And this would be the same value here as well, isn't it? So that's the T filter. Now, if you go over here and you want to get these values, right? We're going to do the low pass filter. Just listen to this though, don't mess this up. Now I have to put the pi low pass filter before I do the transformation. Y'all follow me in this? So I'm going to bring that one back up. And erase this. The biggest problem you're going to have with any of this stuff is just keeping track of how to get the right low pass filter first. Then after you get those elements, the transforms pretty much do themselves, even for the band test, it's not hard at all. So over here, now we're going to start with that. That's the high pass, the low pass equivalent, so that's this. Alright, but I'm going to put the G values down for this. So remember, this is G1, right? That's G1. This is G2 now, the middle element. This is G3. Alright, G1 was 1.0. It was 1.035. Is it 1.5 or 5.1? It's 1.5. 1.5? G2 was. Yeah, 1.1474. We know G3 will be equal to G1, so I'm just going to leave it there. Okay. Now, next, after that, we're going to go ahead and get the values of this capacitance, C prime, not C double prime, just the value of the normalized capacitance value. So, to get this capacitance right here, which is C prime, this will be my L prime. C prime is going to be G1 divided by Z naught. You all with me on that? And Z naught's 50. We'll get that value in a second. This L prime is going to be equal to G2 times Z naught. And if you give me this value, I appreciate it. Pardon?
Prime is 0.02063.
0.02063. Is that right? Can you do that? G1 is 1.0315 divided by 50, is that what it is? Not 0.023? What? I'm sorry. And what is this one? G2 is 1.1474 times 50?
57.37.
57.37, okay, good enough. And G1 is G3. Now, to get the values of the equivalent over here, we take, here, we're doing this one now. Okay. Follow me on this one? This is a pi, that's a pi. So, the reason it's called pi, because it looks like pi. That's the only reason they call that filter a pi filter. So now, we use this value, C prime, to get this value, L. And we find out that value of L is going to be equal to 1 over omega C times C prime. And can you give me that? This, I don't think he has this answer in the book. He uses just the T filter here, but what do you get for that one?
For L?
Yeah.
3.857 nanometers.
And for C here, this value of C is going to be equal to 1 over L prime divided by omega C. So you can tell me what that is.
1.38.
1 point what?
38.
Picofarads. Now, in his book, because I'm trying to make sure he has access to this. All right, he doesn't show you the values for this one, but that's how you would get them, basically. Y'all follow me? And again, it starts always with a low-pass filter. Now, if we're doing a band-pass filter, just listen to me on this one. We always start with a low-pass filter design, but there's, again, 2 of them that can happen. So for band-pass filters, I'm going to explain something. We'll do some problems in the book, because that way I think it would help. So he shows you in his book, on page 590, how he goes about and creates the band pass filter starting with a low pass. And again, there are 2 types. So remember, you can always have 2 configurations. You can have a T configuration, like such, with these just representing T elements. This is a T-type configuration for the filter, or you can have the pi configuration here. Are you with me? Let me try this approach. For this, anytime it's a low-pass filter, this is an inductor, this is an inductor, this is a capacitor. That should make sense to you. Anytime it's a low-pass filter down here, this is a capacitor, that's an inductor, that's a capacitor for low-pass. Anytime you have high-pass, the components reverse. For a low-pass, that was an inductor, this will be a capacitor. For a low-pass, that was a capacitor, it would become an inductor, this would become, that inductor would become a capacitor. Same down here. Anytime you have, for high-pass filters, this would be an inductor, this would be an inductor, that would be a capacitor. This is a bad design, remember that. Because the inductor's in parallel with whatever you're feeding. And that means no DC biasing possible. So those are the 2 types of configurations for band pass filters. When you have a band pass filter, you're passing over a narrow band of frequencies, and what you want is a series LC circuit here, because at resonance, an LC circuit looks like a short circuit. Y'all follow me? Here you want a parallel LC, because at resonance it looks like an open circuit. Everybody follow me on this? Over here you're gonna have the same thing as this. It'll be a series, and then it's a series LC. Over here, what happens here? Parallel elements, you always want the impedance to go to infinity at resonance, so it has to be a simple. These are going to be parallel, or they call them tank circuits, I think. I don't know if you've heard that expression. And this is going to be a series. Okay? Just get familiar with the way things are going to be laid out. So you could have either a T or a pi filter in this configuration. The values you're going to get are going to be based on a low-pass filter, first design. That's the way Whitworth did it. Doesn't have to be this way, but I think in retrospect, he's probably right about this. So if you have your books and you look at page 590, what he does is he starts with a low-pass filter design. We're going to do this one. So this is example 1017 in his book. And he look right over here. So for that example, he gives us a value for, I didn't say this. Whenever you have bandpass filters, there's one thing that's critical. You have to know the upper frequency and the lower frequency. So there's omega upper, the upper frequency minus omega lower, and that is called the bandwidth. But I think this is kind of common sense. You've had this kind of stuff. You have that. If you're an engineer at this point, you've had this. It's just the bandwidth that we're talking about. Then you're going to have something called omega zero, which is just the geometric mean of these two. I'm sorry, it's the product mean of these two, which is omega mu times omega lower. So, and again, for this, omega is 2 pi f. So it's the upper frequency times the lower here. And you're going to get omega naught. Then, once you have those two, you're all familiar with bandwidth, right? Whenever we have filters, you've had, I don't want to get into Q right now, but you know, there's the quality factor and stuff, but there was a bandwidth that you were familiar with, correct? For any kind of a bandpass filter. So after that, when we have those values, we start with, well, let's just do this one. This is example 1017. He wants a third order Chebyshev bandpass filter for a 50 ohm system. So we have Z naught equals 50 ohm. And he wants the number of elements is 3, which is great. And when it says 3 elements, it means 3 blocks of elements, not 3 singular values, right? Because here this pass bands or band stops. And what else does it say about the ripple? And 1 dB of ripple. All right, now, after that, we'll do the he wants to do this one. This is going to be his low pass filter. He's going to have this design. So we'll get these elements in 1 second. And first of all, since this is 1 dB of ripple, I can look this thing up. So I get 2.0236 and 0.9941. So G1 equals G3 equals 2.236. And G2 is equal to 0.99 something. 0.9941. All right, now, remember, this is associated with G1, this with G3, and this with G2. You all remember that? So, first we get the normalized values. We don't divide them by omega C. So, how do you get this C prime? What do? It would be G1, right? Divided by Z0. Correct, everyone? This is going to be equal to L prime is going to be G2 times Z0. And can you give me this value for C prime right here? That's 2.0236 divided by 50. And then L prime would be 0.9941 times 50. Good. I 1/25. Anybody?
Your C prime is 0.04. I got 0.0405.
Okay. And for L prime?
49.71.
Okay. Now, once we have those values, those are the low pass prime values. Do y'all follow me? Not the double prime, they're not the actual values the filter would have when you get it, because that's dependent on the omega C. Then, if you take a look in your book, and this is going to be on page 587, mark this down. So now you look at this, and this is a band pass filter. So for a band pass, you see how the series elements will have L prime over the bandwidth? By the way, we didn't get the bandwidth here. What is that going to be? That's, I think his upper band was, F upper was, I think, 1100 megahertz, and F lower was equal to 900 megahertz. Is that right? Okay. So that means this right here, the bandwidth is going to be 2 pi times, and that's 200, so it's times 200 times 10 to the 6 hertz. So it's 4 pi, really times 10 to the 8th, and that's fine. 4 pi times 10 to the 8th radians per second. And the geometric mean, since now this is going to be square root of 2 pi, F upper is 1100 megahertz times 900 times 10 to the 12th. So what is that? That's 10 to the 6th square root of 2 pi times 1100 times 900. And what's that value going to be? Because we need these values. Anybody? I'm just trying to get you to work this thing with me, because he has for omega naught 6.25 times 10 to the 9th. Is that right? For this omega naught? This should be 2 pi squared, pardon me. This should be 2 pi squared. So 6.25 times 10 to the 9th, I think, radians per second, but you can check. And then the bandwidth on this is 4 pi times 10 to the 8th radians. So now, if you take a look at that, we've got our values for C prime and L prime. And if you look in his book, Now, we're gonna go ahead and get the values for the C and L that are in series and parallel. Now, do you all have your books or not? Most, how many do? All right, well, that's good. If you don't, this is on page 587, but I'm just gonna tell you right now, if you don't have your books, don't worry about it. But if you look there, now, you're gonna see anytime we have series elements, we get the L prime, and that would be here. That's L prime. And we divide by the bandwidth to get the actual value of L. So, let me do it this way. When I'm going here, and I want the value for this L right here, this is going to be true L, there is going to be L prime over there, divided by the bandwidth. And the value of C prime there is going to be the bandwidth going to be the value of C here is the bandwidth divided by omega naught squared L prime. And you have to understand, what I had to do is make sure, wait a second, I'm sorry, not for this one, I got the wrong configuration on that. Sorry, it should have been this configuration on there. You see how this is the pi? So over here, the values for the series one, right here, it would be, this value L prime would be equal to, this L would be equal to L prime over the bandwidth. And the value for C here would be equal to the bandwidth over omega naught squared L prime. And here for the parallel ones, the value of C is going to be equal to C prime over the bandwidth. And the value for L over here is going to be equal to the bandwidth over omega naught squared times C prime. So, I know this is kind of a pain. Starting with low pass, we get the prime values for L prime, C prime over here. Then, since it's a pi configuration, you come over here, and the parallel elements here, you get the C prime that we have there, divided by the bandwidth to get the exact value. You can take the bandwidth over omega naught squared C prime to get the value of L. For the series elements, we use that L prime in the center. We use the one that's associated with G2 and take that L prime over the bandwidth to get this value, and then the bandwidth over omega naught squared L prime to get that value of C. And I want to tell you, I know there are tools that do this automatically online, but you should at least be somewhat familiar with this, because in the real world, you're going to hear people discussing Chebyshev versus Butterworth filters and the benefits and sort of drawbacks to all of them. So I'm over it already. I didn't mean to go that far. I'm going to give you, you've got the homework problems. I may have one or two others. So for Friday, we'll do the quiz at the end, and it will be on this stuff. But I'll go you one better. I'll give you an open book. I don't think I've ever done that in this class. I don't think I've had, but I'll do that. I was going to print out the tables, but you got them right there, okay? So get familiar with using them. Do the problems. You shouldn't have any trouble. I will say one thing about this. I probably am not going to give you a band pass or a band, for band stop, you just replace this with now the series elements here become parallel, and the parallel elements are in series. Band stop. I would probably be high pass or low pass. I'm just level with you. I don't want to cause you too much of a problem, but you should be fine to do the homework and understand it, okay? See you on Friday. And we'll go through a wrap up to the final, and also your projects are due. Last day of class, right? If you got questions about your project, you come to me or send me there.
Print it out, right?
Well, I've got a place where you upload your code. All right, you can do this on